Yes, Assalamu alaikum and good evening. Today we are going to start paper 5 A2 May June 2023. Let's start with question number 1. So do understand the question and do focus on the steps. The partition coefficient KPC shows the distribution between two immiscible solvents. Okay, so it's about partition coefficient. The KPC is determined by measuring the concentration of a solute in each. The organic solvent ethoxyethane. So remember, this is the solvent and this is the other solvent, and water are immiscible. A student is asked to find KPC of butane dioic acid. So this is our solute. Butane dioic acid is the solute which we are going to dissolve in ethanoic acid. That is our organic solvent, and dissolve in water. And we have to see that how it's being partitioned between these two solvents. Okay. The expression for KPC when butane dioic acid is in equilibrium between ethoxyethane and water is shown. Okay. So here we have the expression. We have ethoxyethane dissolved in ethoxyethane in the numerator, and in water it's in numerator. Okay. Now, density ethoxyethane is 0.71 gram per centimeter cube, and water has a density of 1 gram per centimeter cube. So they have given us the density of both the solvents. Okay. The student uses the following method to find the partition coefficient. A diagram of the apparatus is shown in figure 1.1. Okay, you have to keep and you need to keep the follow on the steps. Add 30 centimeter cube of distilled water to a separating funnel. Okay, just give me 1 minute. Okay, weigh by difference 2.81 gram butane dioic acid into a separating funnel. Okay, weigh by difference, it means by initial, first we take the initial difference, and then after adding we take the mass and then take the difference of both the masses. Stopper the separating funnel and shake it until the butane dioic acid has dissolved. Remove the stopper, add 30 centimeter cube of ethoxyethane to the separating funnel. Okay. Replace the stopper and shake the separating funnel gently. Place the separating funnel into a clamp. Allow the liquids to settle so that the two layers can be seen. Like this, if you are observing that, see, there are two layers. Okay, remove the stopper and open separating funnel. Tap to allow the lower layer to run into a beaker labeled A, run the upper layer into a beaker labeled B. So then we have separated both the layers. Okay. Transfer 10 centimeter cube of aqueous layer into a conical flask. Okay. Titrate 0.5 mole per dm cube sodium hydroxide. Use thymolphthalein as an indicator. Take 10 centimeter cube of ethoxyethane layer and add 110 centimeter cube water to it. Okay. Titrate this mixture with 0.1 mole per dm cube sodium hydroxide. Use thymolphthalein as an indicator. So see, we have performed the titration with both the solutions having a butane dioic acid in it, one with the water and one with the water and ethoxyethane. Okay. Now, state whether beaker A in step 7 contains the aqueous layer or the ethoxyethane layer. Explain your answer. So see, if you look over here, water has a greater density than ethoxyethane, right? So if water has a greater density than ethoxyethane, then it means this lower layer is of water and this one is of ethoxyethane. So the first we collected the solution in a beaker, we labeled it A. So this one is going to be labeled A and this one is going to be labeled B. Is this understandable to all of you? So beaker A contains the aqueous layer, right? Not ethoxyethane layer. Explanation: as water has greater density than ethoxyethane. Okay. Number two, identify the piece of apparatus that should be used in step 8 to transfer 10 centimeter cube of the aqueous layer. Okay, in step 8, transfer 10 centimeter cube into a conical flask. So when we have to start the titration in the conical flask, the first chemical we transferred it using a pipette, right? And then after adding the indicator, we transfer the other in a small portion of a volume from the burette. Now, so this is why water is added to ethoxyethane layer in step 9 before the titration can take place. Yes, can anyone suggest the answer? If you read the step 9 over here, when the 10 centimeter cube of ethoxyethane layer has been taken out, we have added 10 centimeter cube of water in it and then titrate it with the mix and titrated this mixture with 0.1 mole per dm cube. Yes, okay. So the thing is that as this is the neutralization reaction, and for neutralization reaction, acid must need to have a hydrogen ions in it. In ethoxyethane, the acid doesn't produce hydrogen ions. So it needs to be dissolved in water before it reacts with the base or before the titration. So the acid dissolves into the water before titration. Otherwise, if it would not dissolve in water, it would not produce hydrogen ions. And if it would not produce hydrogen ion, there is no neutralization reaction would occur. Okay. Now, part B. For a 2.81 gram sample of butane dioic acid, the titer for the aqueous layer is 27.25 centimeter cube and the titer for the ethoxyethane layer is 22.50 centimeter cube. The equation for the reaction between butane acid and sodium hydroxide is shown. Calculate the concentration of butane acid in aqueous layer. Okay. So if you see, we have concluded that this one is the aqueous layer and this one is the ethoxyethane layer. So with the aqueous layer, this is the concentration of our alkali, and here is it's the volume of alkali that has been used, right? And what was the concentration? It's 0.500 mole per dm cube. And the concentration is 0.500 mole per dm cube. And with the ethoxyethane, the concentration of NaOH used is 0.1 mole per dm cube. Okay. This is the volume and this of NaOH, and the solution that we have used over here of NaOH has a concentration of 0.100 mole per dm cube. Okay. Now, so we know the volume of NaOH which is reacted with the aqueous layer, and we know its concentration as well. So if you look at the formula, equation, we got the ratio that it's 2:1 with respect to base and an acid. So first I'm going to calculate the moles of sodium hydroxide. If I calculate the moles of sodium hydroxide, it is going to equals to concentration of sodium hydroxide times its volume. The volume given over here is in centimeter cube, so I divided with 1000 to turn into decimeter cube. Can anyone calculate and tell me the answer, please? Yes, can anyone calculate it and tell me the answer, please? Zero 0.5. Okay, thank you, Maha. It's 0.0136. Okay. So we got the moles of sodium hydroxide. Now we will make the ratio between sodium hydroxide and butanoic acid. This is butanoic acid, right? So 2 moles with 1 mole, that's what we got from the equation. Thank you, Hussein. And if we have these number of moles of sodium hydroxide, then the moles of butanoic acid must be X. So the moles of butanoic acid must be, if you divide it with 2, then yeah, thank you, and it is going to be 0.0068 moles. Now I got the moles, right? Okay. So how much volume of aqueous layer has been used, if you recall? If you see, for the aqueous layer, we have used 10 centimeter cube of a volume. So it means, yeah, thank you, Maha. These moles are in 10 centimeter cube of aqueous layer. So we know the volume, we know the concentration, moles. So for concentration, number of moles divided by volume. This volume is in centimeter cube. So divide by 1000 to convert it into dm cube. Can anyone calculate the answer, please? Thousand, so it's 6.8, 0.68. So thank you, Mohammed Hussain, 0.68. So we got the concentration 0.68 mole per dm cube. Is this clear to all of you? So we have found the Yes, 1 minute, Hussain. We found the concentration of butanoic acid in aqueous layer. Yes, over here, Hussain. Yes, if you see what they have done, they have added 30 centimeter cube distilled water in the flask in the separating funnel. Then they have added 2.81 gram of butanoic acid into the flask, into the funnel. shake it so all of it gets dissolved. Then after this, they have added 30 centimeter cube of another solvent, that is ethoxyethane, in the flask, and then shake it. And then after shaking it, clamp it for some time so both the liquids get separated and settle down. And the butanoic acid, which was initially dissolved in water, now gets dissolved in both of the things. Now remove both the solvents, then take out the aqueous layers 10 centimeter cube and titrated it with the NaOH. Take out 10 centimeter cube of ethoxyethane and titrate it with NaOH. But over here it is dissolved, mixed with the water, so the acid would produce hydrogen ion and the neutralization would occur. Okay, is this clear now? Now, if you see over here, we got the concentration. Now, for a KPC, if you look over here, the expression, in a KPC, we need the concentration of butanoic acid in ethoxyethane and butanoic acid in aqueous layer. So we got this one and we don't know this. So we have to calculate the concentration of butanoic acid in ethoxyethane first, and then we will calculate the KPC. Is this understandable to all of you? So now I'm going to calculate the concentration of butanoic acid in ethoxyethane. So the volume of NaOH is 22.50 and the concentration is 0.1, which is used for ethoxyethane in butanoic acid in ethoxyethane. So first I'm going to calculate the moles of sodium hydroxide is equals to its concentration, which is 0.100, multiplied by its volume, which is 22.50, and divided by 1000. So the volume must be converted into decimeter cube. Can anyone calculate it and tell me the answer, please? Yes, it's 0.00225. So these are the moles of NaOH. If you recall the ratio of moles of NaOH with the butanoic acid, it's 1:2. Sorry, it's 2:1. So if these are the moles of sodium hydroxide, then it's X, so X is equals to 0.0011125. So I got the moles, and for a concentration, 10 centimeter cube of ethoxyethane layer has been removed or used in the titration. So 0.0001125 divided by 10 over 1000 to find the concentration of butanoic acid in ethoxyethane. So multiply by 1000 gives you 0.1.11. It is going to be 0.1125 mole per dm cube, isn't it? So we got the concentration in both now KPC expression. In KPC expression, if you see, concentration of ethoxyethane is in the numerator and the one is in denominator. So it's 0.1125 over 0.68. Now divide it and you will calculate the KPC. Miss, can anyone calculate it and tell me the answer, please? It's 0.165. Okay, so 0.1654 Abdullah. Okay, thank you. So now next part. Explain why the student is only able to repeat the titration in step 8 once. Explain why student is only able to repeat the titration in step 8. Okay. If you recall, how much volume of water is there? Yes, how much volume of water is there? 30 centimeter cube. What is the maximum capacity of a buripipette? And as see, it's a layer over here. So some of both the liquids must be discarded to avoid mixing. So we will not get the exact 30 centimeter cube of water layer. So that's why we are not able to perform more than once. What is the total volume of water? So is it possible that if you see over here that there are two layers, so you have to discard some of the solution from this to avoid the mixing of both the layers in a container when we are separating them, right? So that's why we are not able to perform the titration. We are not able to repeat it. So it is not possible basically uh, to pipette out all the aqueous layer. Now part 4. Suggest how you would modify the procedure to ensure that the student can repeat the titration in step 8 more than once. So it's very easy. You can use the volume of water more than greater than the 30 centimeter cube. We have added this water at the start. So at the start, we need to use more than 30 centimeter cube volume. A different student forgets to shake the separating funnel in step 5. So see why we have why it was shaken. It is shaken to make sure that the the partition would occur and the solute that is dissolved in water can also get dissolved in the butanoic acid as well. Describe the effect this would have on the calculated KPC. Explain your answer. So if you see, if you read the steps again, see, we have added water. Yeah, it gets lower, you can say. We have added water, then we have added butanoic acid, and then shake it to get it dissolved. Now, we have added ethoxyethane and this step has been forgotten. So if it is not shaked over here, it means that maximum of which have to be dissolved in ethoxyethane could not be dissolved. So if the lesser amount of butanoic acid is dissolved in ethoxyethane, so this value is going to be smaller and this value is going to be bigger. So if the denominator gets bigger and the numerator gets smaller, we will get a lower value. And why it is because the equilibrium has not been established and all of the butane acid which have to be dissolved in ethoxyethane would not dissolve. So Effect on KPC? It decreases as equilibrium is not established yet, and water has more butane acid in it. Is this clear to all of you? Okay. Now question number 2. It's paper chromatography. Paper chromatography can be used to separate the individual amino acids formed when tripeptides are hydrolyzed. Okay. One molecule of a peptide produces 3 amino acid molecules when hydrolyzed. Okay. So see, tripeptide, so it means 3 amide links. 3 times C double bond O N links are there. And 3 amino acids when hydrolyzed. Okay. A student is asked to identify the amino acids formed from the hydrolysis of 3 tripeptides, 3 different tripeptides A, B, and C using paper chromatography. Shows the figure 2.1 shows the result of the student's chromatography experiment. Okay. Usual amino acids can be identified from the RF values. Okay. RF value is the distance traveled by the amino acid spot over distance traveled by the solvent front. So if you see the solvent front has a distance of 7 centimeter. Okay. So this is one tripeptide, this is the second tripeptide, and this is the third tripeptide. And here we are getting the signals over there, the spots in the middle of the page. Suggest why each sample is applied to the chromatography paper using a thin layer capillary tube rather than dropping pipette. Okay. So basically the thin layer capillary tube has a very thin tube which has a very small diameter. So from it, you can add a very minute amount of, sample on the paper. So basically it is used to control it. Otherwise, from a dropping pipette, you have to push it, you have to press it from the top, and as a result, it will, more of the liquid can be dropped, and it will, make the paper to tear off. So that's why we use the capillary tube instead of dropping pipette to control the application of a sample, the application of a drop on the paper. It is used to control the amount of sample applied on chromatography paper. Is this understandable to all of you? Now B. Suggest why it is necessary to spray a developing agent over the chromatography paper before the chromatogram can be analyzed. So if you recall, amino acids are colorless. So whenever we are spraying a locating agent or a developing agent, it makes the amino acids spots to be visible. Okay, so it makes the amino acid spots visible. Just give me a minute, please. Okay, till here, is this clear to all of you? Okay, now C part. Table 2.1 shows RF values of some amino acids in the solvent used in figure 2.1. Use the data in table 2.1 to identify the amino acids in tripeptide A. Okay, so let's come over here. In tripeptide A, if you see, it is covering the distance of 1 centimeter. So RF value of this would be equals to 1 divided by 7, right? Because 7 is the solvent front. So can anyone calculate it and tell me the answer, please? What answer we are getting over here? In the same way, if you take the middle of this, it is around 0.13, 0.143. Okay, now over here, so it's 6.5. So 6.5 over 7, and it's 3.6, 3.6, 3.7. 3.7 over 7. Can anyone calculate these values? Zero point 543 is this one, and 0.786 is this one. So we got three values, 0.143, 0.543. Yeah, sorry. Thank you, Abdullah. It's 5.5, not 6.5. Can anyone calculate it and tell me the answer, please? No, it's not. I have mistaken over here. See, it's not 6.5, it's 5.5. So 0.786, Maham, you can check it as well. So 0.786, 0.543, 0.143, right? So 0.14, it means one is lysine. 0.786 and 0.54, 0.54, 0.5 tryptophan, and 0.7 leucine. See, is this understandable? So lysine, tryptophan, and leucine. This is important. Suggest why the hydrolyzed sample of B produces two spots. As they have told you that it's a tripeptide and 3 amino acids are getting, but here you are getting only 2 amino acids. So what does this mean? So it means that the 2 amino acids are exactly the same. not the different one. That's why they have the same RF value and their spots are overlapped on each other. So two of the amino acids are same. Now, two of the spots from hydrolyzed sample C overlaps. State the reason for overlapping. So if you see these are overlapping, so it means they have a similar RF values. And remember, we are not going to use the term same because they are overlapped like this. So their RF values are not exactly same. There is a minor difference. So similar RF values. Now, suggest an improvement to the method would allow the overlapping spots to be distinguished clearly. So you can use a different solvent. So using a different solvent, because it's not necessary that every substance has a almost same solubility in each solvent. So in the different solvent, the both which are overlapping with each other must have a different solubilities. Is this clear to all of you? Okay. This paper has a 3 questions. Okay. Now question number 3. A scientist is asked to find the rate of decomposition of an aromatic diazonium compound and determine the order of a reaction with respect to the aromatic diazonium compound. The scientist is given 1.02 gram of an organic diazonium compound in a 50 centimeter cube beaker. Describe the steps the scientist should take to make 100 centimeter cube of standard solution containing 1.02 gram of this compound. Give the name of and the capacity of apparatus scientist should use. You write your answer using a series of a number of steps. So that is the same thing that you do in the lab. The total volume that you need to prepare is of 100 centimeter cube. So what you will do, take a small amount of distilled water in 50 centimeter cube beaker and dissolve 1.02 gram of an aromatic compound in it, aromatic diazonium. Compound in it. Is this clear to all of you? Then what we will do? Transfer the solution and washings to 100 centimeter cube of volumetric flask, because you know that the volumetric flask is the one which is used to prepare the solutions, right? Then fill the volumetric flask up to the mark with distilled water. That's exactly the same thing that you performed in your labs. If any one of you has any confusion, please ask. And after filling it, mix it well. Okay. Now B. Benzene diazonium chloride and aromatic diazonium compound decomposes in solution to produce phenol and nitrogen gas. Okay. The scientists form 50 centimeter cube of a solution to 50 degrees Celsius. The scientists record the volume of nitrogen gas produced at different times during the decomposition. Identify the piece of apparatus that should be used to maintain the temperature of the solution. So to maintain the temperature of the solution, we always use thermometer. statically controlled water bath. Why I'm using that water bath? Because see, the maximum temperature we need is a 50 degrees Celsius. So that's why water bath, because water on water in water, we keep the temperature below 100 degrees Celsius. Okay, now identify the dependent variable. So the dependent variable, the temperature is the independent. Okay, the dependent variable, it's the volume of a gas because it depends upon the amount that we are being using. Yes. Thank you, Shah. Volume of gas produced or volume of nitrogen produced. So this is why scientists does not monitor the reaction by measuring the loss in mass. Yes. It's not possible because the apparatus or the container is in water bath, right? We have put it in water bath, so how we will measure it, the change in mass for that. Yes, the dependent and the independent variable. Yes, the independent variable is the one which we are choosing on our own, and as a result, whatever the result we are getting is the dependent variable. For example, if eh, I'm using 50 centimeter cube, right? So it's on us that it's not necessary. I can use 50. It's by choice. We can use 60 or we can use 40 centimeter cube, right? So it's the choice that the scientist has made. So it is the independent variable. And we know that they have told you that on heating, the nitrogen gas is produced. So the volume of nitrogen basically depends upon this. If I'm using this volume, then the volume of the nitrogen I will get will be different. And when I use this volume, the volume of the nitrogen I will get will be different. So see, the volume of the nitrogen is basically depending upon this volume, right? So the volume of nitrogen becomes is dependent. Is this clear, Mariam? Okay. Now C part. Table 3.1 shows the results of the experiment. Okay. V final is the final volume of nitrogen gas measured once the decomposition is complete. So it is this. Vt is the volume collected at time t. Okay. V final minus Vt is proportional to the concentration of a benzene diazonium chloride. Okay. So these are the Vt values. Can anyone subtract the values and tell me the answer for this? It is going to be 57.2. Okay, thank you, Shan. 39.9. Then 57.2 minus 27 is going to be 29.8. No, 30.2. 30.2. Okay, 57.2 and 39.5. 17.7. 57.2 and 46. 42.6. 14.6. 8.2. And the last one, 4.4. Okay, thank you, Sean. Okay. Complete table 3.1, we are done with. Plot a graph on grid figure 3.1, show the relationship between V final minus VT and time. Use a cross to plot the graph. Draw a curved line of best fit through the plotted points. Okay. So at 0, it's 57.2. So 57.2. 57.2 is almost like this, right? Then on 17 point, it's the time over here, okay. On 5, it's 39.9. So it's 39.9 means it is like this. And then at 9, it's 30.2. So 9 is this one, and it's 30.2. So it is going to be like, no, 30.2. It is like this. And then at 16, 17.7. Okay, this is 6. No, this is 16. And it's 17.7. So 15, 16, 17. It is like this. And then after 16, we have 21 and 14.6. 21 and 14.6. So 14.6. And then 28, 8.2. So 28 and 8.2. Okay. Then 36, 4.4. 36, 4.4. So 4.4. Okay. So if I try to draw the curved best fit, one. Yeah. So if we see the most, this would be the line of best fit curve. Now, circle one point on the graph that you consider to be most anomalous. So if we will look over here, almost all the points are on the line except this one. So I'm going to circle this plot. Is this understandable? Now, suggest one reason to explain why the anomalous point you have to the explain the assume no error was made in the measurement of volume. So it means what they are trying to say that this is correct, right? So if this is correct, then it means that the time over here must be this, not this one. Is this understandable? Anomalous point is the one which is away from the line of best fit. So is this understandable? So if you see, if the volume is correct, so it means that volume must be on this point, right? And this is the change in volume, not the actual volume. So it means that the volume that we have measured over here is actually recorded before the time. The volume recorded before the time. Now, use your graph to find the first two successive half-lives for this reaction. State the coordinates of both points you use in each of your calculations. Okay, 1 minute. Yes, what you didn't understand? Okay, so see over here, it if the volume is not changed, so it means that the value doesn't change on y axis, right? So it means that this must be on this time. But if you see, this is change in volume because it's saying v final minus vt. So it's the change. So for example, let's assume this value. What is this value? This is, let's suppose, it's around 14.4. Let me check this value. It's 14.6, right? So that V final minus Vt is 14.6. V final is 57.2. So 57.2 minus volume at which at that time it is recorded is equals to 14.6. So volume over here, if I record the volume, the actual volume that recorded over here is 57.2 minus 14.6, and if you do this, it is this volume 42.6, right? So basically, this volume is actually not recorded at this specific time. Okay. So the time that is noted down over here is before the actual time, and that's why we are getting this line this point over here on above the graph, on above the line. Now you have to find the order of a reaction. And for the half-life, we always able to find the order of a reaction. So let's see how you will calculate the half-life. They ask you to calculate the two successive half-lives. Okay. So the first one, what is the initial volume? It's 57.2, right? So can anyone take the half of 57.2? It's 28.6, right? So 26, 27, 28, 28.6 is going to be over here. So we are getting the time 9.5 for first half life, right? Now what is the half of 28.6? It's 14.3. So 14.3. Going to be over here. So if you see here, I am getting 9. If I'm not wrong, I'm getting 19.5. So 19.5 or 19.5 minus 9.5. No, it's 9, not 19. It's 9.2, 19.25. No, 1 minute. There are two boxes. So here it's if you see, it's 9.75. And over here, if you see, it's 19.60. So 19.60 minus 9.75. Can anyone tell me the range over here? What is the difference I'm getting? So see, the first half-life is 9.75. What is the difference over here? So see, the second half-life is also 9.85. So we are getting the similar half-life. It means that the order is first. Is this understandable? So first half-life, the coordinates that we have chosen is 28.6. There is no third order for a specific one. For second order, the half-life decreases, and for zero order, the half-life increases. No, for zero order, the half-life decreases. For second order, the half-life increases. The half-life almost gets double. So the coordinates are 28.86 and 9.75. And over here, the coordinates are 19.60. No. Okay, in coordinates, we first write x and then y, right? Or we first write the y-axis. I always forget that. Yes, which axis we write first? Okay, so over here it is 9.75 and it's 28.6, right? And then 19.60 and 14.3. So here I am getting the half-life of 9.75 and here I am getting the half-life 9.85. So order is first. Okay, and explanation. The half-lives are constant. Is this understandable to all of you? Thank you, Hammad. Okay, so inshallah we are going to do another paper tomorrow. Okay, so see you everyone tomorrow, inshallah. Take care and goodbye. Allah Hafiz. Yes, Azif. Yeah, it will be little difficult, that's why. Yes, Azif, you can see the graph. I have to check the threshold, Abdullah, for this one. Okay, take care. Allah Hafiz.